Hi everyone, I am Jack Clark, AssayQuant's product manager. Thank you to anyone and everyone for tuning in to watch our Senior Director of Discovery Technologies, Earl May, talk about AssayQuant's PhosphoSens technology and its continuous direct catalytic platform, where you can see a progress curve in every well. Today, Earl will give a presentation titled Time-Dependent Inhibition Workflow at AssayQuant, where he will elaborate on the importance of kinetic data needed to understand time-dependent inhibitors. We would love to take your questions in real time, but obviously this is a recording, so we can't do that. Please write down any questions or thoughts you may have during the presentation and contact us directly at hello@assayquant.com for an answer. We look forward to hearing from you. The floor is now yours, Earl.
Thanks a lot, Jack. I'm going to talk to all of you today about how we handle time-dependent inhibitors using our assay system. And this is how we run things in-house, but it's also how you could run it if you actually have our bulk reagents and want to do this in your own shop. So before I go any further, I want to just flag for you there's an excellent source for a lot of this information that I'll be presenting today, Bob Copeland's book on the evaluation of enzyme inhibitors in drug discovery. So with that, I want to review with you the assay platform that we use at AssayQuant, the PhosphoSens technology. So this assay depends on peptide substrates where we have linked a fluorophore within 2 to 5 residues of the actual phosphorylation site on the peptide substrate. And these peptide substrates are otherwise fairly biologically relevant here. So when the kinase phosphorylates this peptide substrate, that allows for a magnesium to be chelated between the phosphate and the SOX fluorophore, and that chelation, the fluorescence is enhanced by that chelation event. And we can monitor that increase in fluorescence as a function of time. And that this assay is direct, it's homogeneous, and it's continuous. And so in the end, you actually, as Jack said, get a progress curve in every well. And so we use this technology in a lot of different purposes here. Okay, we can do it in any kind of well and just about any kind of plate reader. Very likely you have one in your shop that can do it right now. We use this assay system that I just described, and we get this progress curve in every well. And you can actually watch this develop as every 14 seconds to a minute or however long you've got it spaced, points are added to the progress curve as this goes along. And we can use this to do kinome profiling. We have 376 kinases at present, and that's ever growing. We can actually do this not only on just isolated biochemical assays, but we can do this in tissue and cell lysates as well. And that's something we're currently developing. But the focus of this presentation is going to be how we use this platform to look at inhibitor potency. And so that's both straightforward IC50 generation, but more importantly, because this is a continuous assay system, it's really ideal for evaluating time-dependent inhibitors, which is really where it's at in an awful lot of drug discovery campaigns that are going on right now. So before I go any further, I want to, so that's where we're focusing today. So before I go any further, I really want to contrast what I mean by continuous assay format. By and large, the vast majority of enzyme assays that you use in your lab and that folks use are endpoint assays, and those are all terrific. But just you have to bear in mind that there's a fundamental assumption in endpoint assays. You do a reading at a specific time point, and you're assuming that reading estimates the initial reaction rate. Okay, so you're assuming that the rate goes from 0 at 0 time to your endpoint, that signal at that time point, and you're using that to estimate the slope in all of these things. And that's all great if you've actually verified that you have a progress curve that is linear with time and that goes through the origin after you've subtracted the background. The thing is This is typically not the case for a lot of enzymes, and kinases in particular. You could have a significant lag at the beginning of the progress curve for a number of reasons. We do our best, and we are continuously trying to improve to minimize that lag, but it could still be there. And then also, for a whole bunch of reasons, the curve could saturate towards the end of your reaction. And if you're relying on an endpoint assay, these variations from linearity, either at the beginning or the end, or even in the middle sometimes, could greatly mislead your structure-activity relationship campaign and confuse your medicinal chemists. And on top of all of that, there are some fundamental interesting characteristics of the compounds that you could exploit in your drug discovery campaigns that you might totally miss if you're only doing endpoint assays. But even if it is linear, even if it's straight line from your endpoint to zero, and you've verified all of that, you get a 2 or 3 replicates of your endpoint, and that's as much confidence as you have in that estimated initial reaction rate. With our assay, you're actually generating rates from many time points in the linear portion of the progress curve. So our confidence in the rates that report is much higher. So we will do them in duplicate and triplicate sometimes or more, but really the rates that we're determining, we have much higher confidence in. So everything that I've just said here is really important for all types of inhibitors, but really when you're working with time-dependent inhibitors, that's where it gets especially important. So what do I mean by time-dependent inhibitors? This is what I mean by an endpoint assay. Let's say you're doing a 1-hour endpoint assay and you're just getting the signal here at 1 hour. That's great. And it's a straight line back to the origin for all of these. There, it is perfectly reasonable to assume that that signal is a good estimate of the initial reaction rate and do your dose response curves and anything else that you want to do using that value. And that makes it just fine for this type of a binding reaction where your inhibitor, your compound, is binding to the enzyme to form an enzyme inhibitor complex. And you've got an on rate and an off rate, and the IC50, you can use that to calculate a KI, which is a kinetic estimate of the KD that you would get from this, which is the off rate on the on rate. All that makes sense. You learned all about that in your basic biochemistry classes. Now, if they're not linear and they look curvy like this, where there is an initial rate, but it keels over as the rate goes along, well, what do you do with an endpoint assay here? The IC50 that you get at this point of the curve could be very different from the IC50 you get at this point of the curve. It's as if the inhibition is actually dependent upon the time of the reaction. So those are what we call time-dependent inhibitors. And the easiest way, not the only way, but the most typical way that people describe this is that there's an enzyme plus inhibitor that forms an initial complex, and then something else happens, a conformational change, some sort of a variety of things to form a second complex, okay, which is more stable and has a slower off rate here. So enzyme plus inhibitor forms this complex, and then over time, this complex transforms into this complex, which has a slow off rate. That is at its core time-dependent inhibition. So at AssayQuant, we work with inhibitor. We have a workflow, a standard workflow that we go through this. And I'm going to step through this slide in detail. And it's something you can use in your own labs, but it's an example of what we do here. So first, we start with an inhibitor that we don't know anything about. The first thing we're going to do is just do a standard dose response experiment. And like I just showed you, here are linear progress curves, and here are curves that are keeling over. If they're linear progress curves and look like that, that suggests there's no time-dependent inhibition there. And so we can just do our standard 4-parameter fit analysis to generate an IC50, as well with the Ymax and the Ymin and the hill slope. And then if we have the other important information that we need to generate a KI, we can report all of that information to you with a fully reversible, non-time dependent inhibitor. However, if they look like this, then it gets a little tricky. This suggests that they're time dependent. And here's where the next step in the process is critical. We need to find out whether these time dependent inhibitors are reversible or irreversible. And we do that through a reversibility experiment, which I'll go through in detail over the coming slides here. That involves first doing a IC50 analysis both with and without a enzyme inhibitor pre-incubation step. And then we use that IC50 in a jump dilution experiment, which I'll describe in a second, which will tell us if it's fully reversible, if it's reversible but with a slow off rate, or if it's fully irreversible. If it's reversible, then we can actually do either forward progress curve analysis, or more likely what we do nowadays is a global fit to a jump dilution analysis at a number of inhibitor concentrations. And from there, we can report the off rate, we can report the half-life of the complex, and we can also report the residence time, which in the literature is often symbolized by tau and all of this. If, however, the reversibility experiment tells us that it's irreversible, then we're going to do full forward progress, very detailed, full forward progress curve analyses, and not be reporting IC50s. We're going to be reporting kinetic parameters, kinact and ki, which I'll tell you about in a bit. We'll always be able to report the ratio of kinact on ki, which is the most important parameter for describing irreversible inhibitors for SAR. But if it's possible, we'll actually report kinact and ki separately as well. So just one further note before I go on from here. It's important to note that not all irreversible inhibitors are covalent, okay? And not all covalent inhibitors are irreversible. So the covalent and irreversible are not synonyms in all of this. So just bear that in mind. There are reversible covalents, and there are irreversible inhibitors that are not covalent. All right, so let's get into the details about those two different types of time-dependent inhibitors. If you eyeball the curves and you look at them, and there's an initial rate that looks like this, and then there's a final rate that looks like this, right? That is more often than not a reversible but slow off rate inhibitor. And you can actually use this rate constant, which describes how quickly it takes to get from this rate to that rate. You can use this rate constant to actually estimate the off rate. And I'll get to that in a second. If you look at this, and rather than ending up at a steady state velocity that's non-zero, okay, if it actually looks like this, where the steady state velocity is 0, all right, that means that the K6 is 0 in this, the off rate from this complex is 0, and it comes down to this type of an equation, all right, where there's a rate constant here, and that's kinact. I'll tell you in a little bit, and there's another value parameter here, ki, that describes all of these rate constants here. That is all suggestive of an irreversible inhibitor. And so just eyeballing it, often you can tell this suggests it's going to be reversible. And the fact that these are all plateauing at 0 suggests that it's irreversible. But really, to verify that, you have to do a reversibility experiment. And there are 2 steps to your reversibility experiment. As I said before, the first step is you got to get an IC50 with and without that pre-incubation step of the inhibitor with the enzyme. And you use that IC50 with the pre-incubation in all of the jump dilution reactions that you do. Critically, you would use that and you would pre-incubate the compound with the enzyme at a concentration that's 10-fold over its IC50. So that's just a pre-incubation. You haven't started the reaction yet. And then after an hour or so, you dilute that reaction 100-fold into substrate that actually starts the reaction. So you pre-incubated at 10-fold over the IC50, but now you're 10-fold under the IC50. And you want to follow the recovery of the enzyme activity over time. Okay, and you're going to compare this activity with controls. You'll have a control where you basically pre-incubated at 10-fold under the IC50 and then done it, and then pre-incubated at a concentration of 10-fold over the IC50 and then start the reaction. Neither of these are jump dilutions. So these are just the controls. I'll reiterate this in the next couple slides. So now you look at your data. If you don't see any recovery at all over time, that means the compound is not coming off the enzyme. It's an irreversible inhibitor, or at the very least, it's an inhibitor that is not coming off the enzyme during the time frame of your experiment. All right. If it actually looks like you didn't do any jump dilution at all, and it looks like a progress curve that you would see if you pre-incubated at 0.1 at 10-fold under the IC50, that means it's fully reversible and it has a fast off rate. And then finally, if you see a slow recovery over time, that means that it is fully reversible, but it takes a while to get there. So there's a slow off rate in all of this. And this is where the power of the PhosphoSens assay really comes in. That continuous assay format means that you don't have to set up time points and do the complicated reverse reaction setup, and you're not limited by 6. Now you've got, you know, a time point every 10 seconds to a minute, and you're monitoring this over, you know, the entire reaction time that you have it on the reader. So a really good reversibility experiment, like I said, you start off by getting that IC50 with pre-incubation. And in the jump dilution experiment, this is what I described to you. You watch for the recovery of activity over time. Very important, though, you also have the controls here. All right, you have the control where you've got it, the concentration of the inhibitor is 10-fold over the IC50, and a control where the inhibitor is 10-fold under the IC50. And the progress curve for the jump dilution, this slope at the very beginning is the very same as this control slope, and at the end, this slope is exactly the same as this slope, which is 10-fold under the IC50. And so now it's all about determining the reversibility. If it looks like this, that's a slow off rate reversible inhibitor. If it's right on top of the 0.1x IC50 line, that's fully reversible and very fast off rate. If it's right on top of this control, then it's in essence irreversible, or so slow that you can't tell in this part of the reaction. Now, if it does have a slow off rate, if it does look like this, okay, then this initial velocity will start here and the final velocity will end there. And if you can determine this rate constant here, you can actually determine the residence time of that slow off rate inhibitor. How do we do that? Well, again, we're going to do it through jump dilution analyses. There are other ways that you can do it that we're exploring, but this is pretty much the most accepted way of doing it now. You set it up. You set it up the same way as you do your jump dilutions experiments. You use the IC50 from the pre-incubation experiment, and you have your controls at 10-fold over and 10-fold under the IC50 here. But you need to do it at a number of different concentrations. So here we are at 15-fold under the over the IC50 and ending with 0.15 at times the IC50. And then we'll also start at 5-fold the IC50 and go to 0.05 times the IC50. So we'll look at all of these rate K observed that are determined from here, and look at these. And here's the important part. And if you want further background on this, I recommend either this Copeland paper, which I've extracted this paragraph from, or Bellbrook Labs has a nice technical note that I would recommend you take a look at as well there. But the trick is the rate constants that you get here from these various concentrations, you want to use the rate constant that you can determine from the smallest inhibitor concentration possible. And that minimizes any contributions of rebinding, okay, of the inhibitor to the enzyme that would complicate your K observed calculation. And if you're confident that you've got the lowest inhibitor concentration where you've got a measurable K observed, that is a good estimation of the half-life itself. Okay, so that K observed value can be used to approximate that off rate there. And with that off rate, you can calculate the half-life and you can calculate the residence time. And those are two different measures that are just related by a log of 2 in all of this. A lot of people like to talk about resonance times, and a lot of people like to just talk about the half-life of the complex. So if it's fully reversible but a slow off rate, this is a good way of getting resonance time, which is a great way to guide your SAR for inhibitors of this type. Now, reporting IC50s for reversible time-dependent inhibitors, you can do that, but definitely if you do that, you want to use the slopes that are from this portion of the curve, okay? These slopes here, that final complex, that's the complex that's most indicative of the potency of this class of inhibitors, all right? If you use IC50s at the beginning of the reaction or in the middle, then you could greatly underestimate your potency in all these things. And again, if you're trying to do this with an endpoint assay without any time points, you don't know where you are in this. So you could do an IC50, just make sure you're in the steady state portion of the progress curve. But really, it's best to do the kinetic workup that I just showed you on the previous slide and report those resonance times or half-lives, and that gives you SKR rather than SAR. It's actually a structure-kinetic relationship. All right, so you can actually, from these progress curves, get some instantaneous slopes here and interpolate these IC50s. And to a first approximation, these can be good indications and things you can use for these IC50s. Now, back to reversible versus irreversible progress curves. Here's what I showed you before. And if you just extract one of these progress curves here, you have this initial rate, you have this steady state rate, and then you have the rate constant that describes the change from that first to the second. And there actually is a nice equation that you can use to monitor this exponential decay from this rate to that rate using this this K observed. And it looks like this, where VI is the initial rate, VS is the final rate, the steady state velocity rate, and K observed is this rate constant here. And so it's a e to the minus KT type of exponential equation, and you can monitor this over time, okay? And you can actually use this to actually generate K observed as an alternate to what I showed you before. However, if you actually look at this equation and you say, well, VS is 0, okay, the steady state velocity is 0, it's very similar to this, except that final velocity is 0. And so this equation collapses down to this equation here. All right, well, VS is 0, the initial velocity is there, K observed is there, and so it's a little bit easier. All right, they're both very similar here, similar equations. The only difference is that that steady state velocity is 0 between these two. Now, if you look at this equation here, at this reaction schema, and you start with that equation that I just showed you before, and you plot K observed that you calculate as a function of the inhibitor concentration, you get this hyperbola, okay? And this hyperbola is defined by a y-intercept, which is the off rate of the E star I complex. And the upper asymptote of that hyperbola is the summation of K5 plus K6 here, the on and off rate forming this final complex here, right? And you can fit to this and solve for all of that. This is the actual equation of that hyperbola, okay? If K6 is 0, okay, and that means you have an irreversible inhibitor, that means that K6 is 0, it goes for the origin here. And if K6 is 0, then the upper asymptote is just K5, just K5. And we have a special name for that rate constant there. That's the inactivation rate constant. That's the rate constant that describes the actual inactivation of the enzyme by the inhibitor, usually through a covalent bond that forms there. And this is the very simple hyperbolic equation for this hyperbola here. Okay? So again, plotting the rate constants as a function of the concentration of the inhibitor gives us a hyperbola in both of these cases. All right, so now I'm going to talk strictly about irreversible inhibitors from here on out here. So again, this is what I showed you before, where you've got a good fit to this hyperbola here, and you can actually solve for all of these things because you see the whole hyperbola. You can solve for K inact, you can solve for Ki, and you can report Ki, K inact, and that important ratio of K inact on Ki. The thing is, an awful lot of the times here, if the warhead is very, very reactive, it's super hot, that means that upper asymptote is super high. Or if the binding is very weak, that means that this portion of the curve, the Ki portion, K capital I portion, is shifted over far to the right, then you can only see this linear portion of the hyperbola. And that looks like this. So you can see this portion, but you can't see when it's leveling off. And if you can't tell when it's leveling off, then you can't find the concentration that gives half of that maximal inactivation rate. So if you can fully see the full hyperbola, we call this two-step analysis because we can solve for both K inact on Ki. If, however, you can only solve this linear portion, because the warhead's super hot or the binding is super weak, then you can only see the line. And you know what? That's just fine, because the most important thing that you can get from all of this is the ratio of K inact on Ki, and that's actually the slope of that line right there. So even if you can't extract K inact from Ki, you can usually get a linear relationship between K observed and the inhibitor concentration, and that will give you K inact on Ki. So before I finish up here, let me tell you about the Ks and Is and how all these look here. For reversible inhibitors, I kind of alluded to most of this, but I want to introduce another term. So that final complex there is E star I in all of this. So there's two steps. The enzyme binds to the inhibitor to form this complex, which then there's a conformational change or something else happens that forms a different complex. And that's described by these two rate constants here. The initial binding step, this initial, when you go to E to I to EI, that is your old friend Ki, the kinetic binding constant. Okay, that's so the kinetic binding constant is related to the Kd of the inhibitor binding to the enzyme in the same way that a Km is a kinetic description of a substrate binding to an enzyme, and that Kd for that substrate. So just something to bear in mind. There's actually another collection of rate constants here that doesn't just have the off rate divided by the on rate, which gives you this rate, this Ki. There's Ki star, and that's K4 plus K5 divided by K3 plus K6, and that incorporates all of these various steps. And so that's what these are here, and that's how you can calculate the half-life and the residence time. So that's all the Ks and Is for reversible. A lot of folks aren't as familiar with all of the Ks and Is and such for irreversible inhibitors. So as I said, if Kx is 0, if the off rate is 0, then we call this the inactivation rate constant, or K inact here. And the Ki, the non-covalent rate constant, is still here. It's right here. That's the non-covalent off divided by on that leads to this. And that's still there, but you can't really see this in anything that we're doing here. And so you can't really call it Ki, K little I. An unfortunate aspect of the way enzymology developed over the years, there's a better term for Ki, which we call Ki. It's K capital I in this, and it's an amalgamation of all of these rate constants, K4 and K3 with the inactivation rate constant. It's K inact plus K4 divided by K3, whereas the non-covalent rate constant is just K4 divided by K3. All right, and it's important to separate those out in your mind. So K inact is the maximal rate of inactivation. K big I is the kinetic binding constant that defines the concentration at half the maximal inactivation rate. All right, that's K big I and all of that. And K inact on Ki, that's the inactivation efficiency. And that's the most important parameter for SKR. And that's very related to Michaelis-Menten substrate characterization, like K cat on Km. It's exactly the same math and exactly the same logic that goes into K inact on Ki. Very useful parameter, and that's what folks use. So bear in mind, if you get confused between Ki and Ki, K little I and K big I, you're not alone. It is a major part of confusion that is rife in the literature, and I just encourage you to watch out for this mistake, especially when they start derivations like this, okay? And there's also a lot of review papers that have this misunderstanding incorporated in there. Important to note that there's no mention of any IC50s anywhere on this slide, okay? So how do we actually get K inact and Ki or K inact on Ki for what we do here? We actually have used a method in the literature where we carefully follow all of the progress curves at once. And this is proven to be a better method than trying to plot K observed as a function of the inhibitor concentration. What we do is we do lots of progress curves, 24 of them, with a dilution series that's 1.5-fold, not 3-fold. And then we do a global fit all the way down to this equation, which I introduced to you before. And then we actually fit this to both one-step and to two-step models, as I described before. And then we do a statistical test, an F test between these two models to say which one best describes the data. And this is proven to be the most powerful and the most robust method of extracting the most information we can using our continuous assay format. So if in this example, for example, we have a one-step model, okay, and here are all the parameters that we fit that comes out of this. And here's K inact on Ki. We can't get Ki and K inact and Ki separately with the one-step model. This is just looking at the linear portion of that hyperbola that I showed you before. So that we have standard error associated with all those values, and our confidence for everything as a whole is listed here. We also do the fit to the two-step analysis model. That gives us K inact and Ki separately. Here's K inact on Ki and the standard error to fit here. We compare these two models. We say which one is the one that best describes it, and then those are the data that we report. And that's really the best thing for you to receive. Now, despite all the caveats that we give people, that you can't really give IC50s for irreversible inhibitors, and I'm going to close with a slide on that in a second, people still ask for what is the IC50 at 20 minutes, at 10 minutes, at an hour, whatever. We, for illustrative purposes only, with all the caveats listed down here at the bottom of the graph, we can show you the predicted dose response curve at 20 minutes here. And for those who are old school like myself and used to looking at these kinds of data with this hyperbola, K observed as a function of the inhibitor concentration, we can back calculate that and show you what this would look like if we had done it this way. But again, this is just for illustrative purposes only. Okay, so I'm going to close with a admonition about reporting IC50s for irreversible inhibitors. Okay, we're often asked to do this, and if you see IC50s in a paper that describes an irreversible inhibitor, that's usually your first sign that these people are not fully understanding what they're working with there. Okay, and so when they ask, we try not to. Okay, and we resist. And if our clients still say that they want them, then we're going to give them all the caveats, and we're going to caveat like crazy. All right, so the reason why, these are time-dependent inhibitors, and the time that you actually measure your IC50 will greatly influence your IC50 determination. If it's early, it's mostly just the initial binding event that you're following. If it's too late, then you're just measuring how fast all of the enzyme is inactivated. And in fact, if it's all the way over here and you're only looking at these, all of these are 0. So you can't get an IC50 if it's late enough. It's undefined. And if it's in the middle, you really don't know what's going on there. Okay, so really, some people say, but you know what? I'm always measuring at the same IC50. Though. I'm always measuring the IC50 at the same time point. Isn't that cool? No, it's not, because it really is dependent upon the relationship between the kinetic portion of the time-dependent irreversible inhibition and the K big I portion of that irreversible inhibition. And depending upon which of those things are weighing most heavily in the overall schema and where you are in the progress curve, your whole SAR campaign could be greatly misled by that. Really, it's far, far better to use kinact on KI, that inactivation efficiency, to best describe your structure-kinetic relationship campaign. So that's really all I've got to say for time-dependent inhibitors. I'd like to reiterate, this is how we do things in our house, and it's what we would encourage you to do, and we are happy to help you set this up with our reagents and give you all the tools necessary so that you can do these calculations on your own. So that's it. Back to you, Jack. Can't hear you, Jack. You're on mute. Let's start over.
Technical difficulties, as always.
I'll take a pause. I'll take a pause here. And back to you, Jack.
Yeah, thank you so much, Earl. And yeah, keep it up on this slide because I think it's such an important thing to note. So thank you. Yeah, and just really thank you so much for your time today, Earl. And for any of our viewers who are interested in learning more about AssayQuant and how we can enable your drug discovery and development, or if you had any questions during the presentation, please reach out to us at hello@assayquant.com. We'd love to learn more about you. We look forward to hearing from you, working with you, and have a great day, everybody.